In this video, we will learn on how to solve application involving differential equation. So, altogether, we will learn 4 different types of application. The first 3 application involving Newton's law of cooling, population growth, and radioactive decay. We will solve this by using separable variable method. And then for last one, electric circuit, we will solve this by using integrating factor method. So let's check one by one. So for the first question, assume that the population of Earth changes at rate proportional to the current population. Write the differential equation satisfy this population. So for our population, they didn't mention the name. So it's just a population, general population. I assume it as P. So it's involving rate. That's how it starts with dP over dt because it's rate. Proportional, so equal to constant of the current population. So K times P. K in this case is a constant because it's proportional to. And that's basically our differential equation. Okay, moving on next part of the question. So in 1990, we estimate the population will be 3.9 million. In 2000, our population will be 5.3 million. So by solving the differential equation, fitting this data, estimate the population at time t. Means in this case, we have to find p in terms of t equation. So let's solve this one by one. So before we find t, we must start with our general differential equation, what we find in part A. So we have dp over dt equal to kp. Remember, k is just a constant. So from this differential equation, we want to find p. So we can use separable variable method. Just separate the variable. So if I rearrange this, now we will get 1 over p dp equal to k dt. Yes, we successfully separate this variable. Now we may start integrate both sides. So integral of 1 over p will be ln p. Integral k with respect to dt, we will get kt plus c. Don't forget plus c plus any constant at the back. So now we have to simplify this equation as we want to make p as our main subject on left side. Eliminate ln, so we have to exponent both sides. That's how we get p is basically exponent to the power of kt plus, so it will be multiplied with exponent to the power of c. Why I separate this out? Because next part we have to find the constant. So to make it easier, exponent to the power of constant, I change it as one variable only. Let's say a. So finally, our p is a e to the power of kt. In this case, a is exponent to the power of constant. Now we get our p equation. But we didn't solve what the question asked for yet because we want to find population in time t. But now we have an extra constant here, which are a and k. So what do we do now? We have to find value of a and k to find our population equation. Using the info given in the question. So first info, it says that in 1990, our population would be 3.9 million. So this is the beginning of the observation. So I assume our time is the inertial. So I substitute t equal to 0 here. So substitute this info into our equation just now. We would get 3.9 is basically a e to the power of 0. Means that a will be 3.9. So from here, we may get a new equation, which is p is 3.9 exponent to the power of kt. So settle with the first part, we already find a. Now we have to find k. So in order to find k, use the second info in the question. It said that in the year of 2000, the population is 5.3 million. Okay, so what is t? So we have to find the gap between 1990 up to 2000. In this case, the duration will be 10 years. So T is 10. So substitute this into our latest equation. Just now, what we have find. So now we would have 5.3 is basically 3.9 exponent to the power of 10k. So now we have to find k. Alright, so in this case, please don't use your calculator. We have to find the exact value. We cannot round off our answer. That's why we cannot use calculator. So I rearrange back. Exponent to the power of 10k is just basically 53 over 39. So if I want to find k as our main subject, means we have to ln both sides and then divide by 10. So finally, our k here is 1 over 10 ln of 53 over 39. So substitute the k into the equation. So our latest equation now will be p is 3.9. K is the whole value times t. So I rewrite this as t over 10 ln of 53 over 39. And that is basically our final answer for part B. We have to find population, equation of population in time t. So we have p in term of t. Okay. Moving on, last question. Hence, estimate the population in 2020. So, using the equation that we have found in part B, so to find C, now we have to find what is the population, so what is P, in the year of 2020. So, remember, beginning just now is 1990. The duration or the gap between 2020 from 1990 would be 30 years. So in this case, our T will be 30. So straight away substitute this into the equation. P will be finally 3.9. So T is 30. I substitute into T part here. So it has to divide by 10. So I just rewrite that as 3. Ln of 53 over 39. And now you may start use your calculator to estimate the population. So straight away using calculator now, our final answer, population would be 9.788 million. Okay, settle. That would be the first application. Moving on, next part, we have the second application involving Newton's cooling law. Okay, the question or the statement is quite long, so be careful with it. Under a certain condition, the rate of cooling, okay, rate of cooling here, use the notation of theta. So our differential equation would start with d theta over dt. T represent rate, okay. Proportional, so it's equal to K. Because we have to cool down the object, so we have to put a negative here. If it's about heating, then it's positive K. If it's cooling, then it's negative K. Okay, so K multiply with what? Next statement. Difference between object and room. So difference between, okay, remember that part. So for object, our notation is theta, and then for room, our notation will be theta naught. So we have to multiply with difference between objects, so theta, with room temperature, theta naught. Okay, we have to minus between these two. And that would be our differential equation of Newton's law of cooling. Okay. Given further that the room temperature is 20 degrees. So from this dE, I can substitute the room temperature. So d theta over dt is finally negative K, theta minus 20. So part first, find the particular solution of this dE. Alright, so we can solve this dE first. Just now I just copy back. We start with d theta over dt equal to negative K, theta minus 20. So, in order to find the particular solution, so means that we have to find theta in terms of P. Alright, So separate the variable, same as a population application, we may have 1 over theta minus 20 d theta equal to negative k dt. So we successfully separate the variable of these two. We may start integrate both sides now. So for the first function, we may get ln of theta minus 20. So integrate negative k, we may get negative kt plus c. But remember, we have to find theta, means that we have to simplify that part. In order to eliminate ln, we can exponent both sides. So theta minus 20 is basically exponent to the power of negative kt times exponent c. Exponent c I change as a, but then I mentioned here, a is basically exponent for c. So finally, our theta will be a e negative kt plus 20. And that would be the particular solution. Alright, moving on. Next part B. So, if it takes 12 minutes for the object to cool down from 100 degree, means that our initial temperature here is 100 degrees. So, that's the first info. Remember, initial time, so T would be 0. Temperature in this case would be 100 degrees Celsius. Okay, so 12 minutes to 50. So, means after 12 minutes, when T is 12, our temperature will be 50 degrees Celsius. So, find the time taken for the object to cool down from 50 to 25 degrees Celsius. Means after that, we have to find the T when our theta is 25 degrees Celsius. Alright, so let's solve one by one first. It's basically the same step as population pattern. We have to find the value for A and K, both constant. So using the first info, when T is 0, theta is 100. So I substitute it straight away. We now have 100 equal to A e to the power of 0 plus 20. In this case, our A would be 80. So I substitute it back. Our equation now will be theta is 80 exponent negative kt plus 20. Alright. So settle with A. Now we proceed with K. So next info, when T is 12, theta is 50. So I substitute here. 50 is 80 exponent negative 12k plus 20. Now we have to make K as our main subject. So simplify first. We can minus it with 20 and then divide by 80. So exponent negative 12k is basically 3 over 8. And then next step, ln both sides, divide by negative 12. So k is finally negative 1 over 12 ln of 3 over 8. Okay. Settle that part, we may rewrite our new equation now. So theta in this case would be a t exponent negative with negative. So we can eliminate that part. T over 12 ln of 3 over 8 plus 20. And that would be our latest equation. Okay, settle that part. Now, we have to find T if our theta is 25. Our object temperature is 25. So, just use this equation. Substitute theta as 25. So, we have 25 is 80 exponent to the power of T over 12 ln of 3 over 8 plus 20. From here, simplify one by one to find T. Okay, so we can minus with 20 and then divide it by 8. Alright, so I would have now exponent T over 12 ln of 3 over 8 is basically 5 over 80. And then we can ln both sides. After that, rearrange back to find T. So T here would be 12 ln of 5 over 80 divided by ln of 3 over 8. And then you can straight away compute into your calculator. So our time in this case would be 33.92 minutes. Okay, that's not the final answer yet. Careful here. Why? Why? This is not the final answer. So remember back our initial time when t is 0 just now, it is 100 degree. So what do we find here is actually from 100 degree drop to 25 degree. And that took 33.92 minutes. So next info in the question, it says that from 100 degree drop to 50 degrees Celsius, it took around 12 minutes. So how do we find from 50 drop to 25? Okay, we just have to minus this up. So finally, it actually took 21.92 minutes for the object temperature to cool down from 50 to 25 degrees Celsius. Now, moving on to the third application, we have rate of decay of radioactive substance varies with the mass of a substance. Alright, so now they didn't mention the name of our radioactive, they just mentioned a mass. So I'm just using M here. So start with rate of a mass. So our dE, differential equation, we start with dm over dt equal to K times with the remaining mass, so Km. It's said decay here, so means that it's reduced, so I put a negative. So write the differential equation of this relationship. Yes, this is it. Alright, so if the mass of the substance remaining after 10 years is half of its original, what is the percentage of the substance after 7 years? So in order to answer this part, we have to find the mass equation first. So in order to do that, we have to solve this dE first. Same as before, this is still using separable variable method. So we can separate the variable. We now have 1 over m dm equal to negative k dt. And we may start integrate both sides. So now you already know the pattern. They just follow the same pattern. So I straight away quite fast a bit. 1 over m is ln m equal to negative kt plus c. Finally, m is a e negative kt, where a is basically exponent to the power of c. Alright, we're done with the mass equation, but then still same problem. We don't know yet the values of A and K. So using the first info, they didn't say the initial mass in this equation. So we just assume it. So when it's initial time, mass would be, I put here SM0. And you can use any other variable. Maybe you want to use N or O, up to you. I'm using M0 here. Okay, substitute this up means that m naught now is a times exponent to the power of 0, means that our a here would be m naught. So substitute this back now. Our new equation would be mass m is m naught exponent negative kt. Settle with the first part. Now we have to find values for k. Alright, using the info in the question, it says that after 10 years, so when t is 10, the mass would be half of its original. So if our original is m0, half of it would be 0.5 m0. Or you can put half m0, up to you. Alright, now substitute this info. Now we would have 0.5 m0 is basically m0 exponent to the power of negative 10k. And now we have to simplify this up to find k. So m0 can be cancelled out, no problem with that. And then we can learn both sides in order to find k. So finally, k here in this case would be negative 1 over 10 ln of 0.5. Okay, substitute this into the equation. So now our latest equation for mass would be m equal to m0 exponent to the power of negative here. Alright, I highlight it. Negative and negative can be cancelled out times by t. So we would have t over 10 ln 0.5. And that would be our mass equation in time t. Okay, now we may answer the question. We have to find the percentage. Remember, highlight the word percentage. So what is the percentage of the mass After 7 years means when our t is 7. So straight away, just substitute 7 into the equation. So m now here would be m naught exponent to the power of 7 over 10 ln of 0.5. So straight away, just calculate it using your calculator. We will get 0.616 m naught. But this is just a mass. We have to find the percentage. So just convert this, just convert it into percent form. So we will get 61.6%. How do we find this in terms of percentage? You just remember, you just have to put the mass, so 0.616 m naught, divide by its initial, so we have m naught, times by 100. That's how we get 61.6%. That's why at the beginning, I said that you can assume any variable for initial m naught, because finally, you will have to cancel it out to find the percentage. No problem for that part. Alright, moving on to the last application involving electric circuit. Remember, for this question, we have to solve it by using integrating factor method. So don't worry. For the differential equation part, it's what it is in the box here, the blue box. It remains the same for all question. Okay, so you just have to straight away use this differential equation. Might have few notation, but then I guess you quite familiar with it. So L here in this case will be inductance. And then we have R here. R would be resistance. And then we have I. I is basically current. And last one we have E. E is voltage. Okay. Normally for this type of question, values for inductance, resistance, and voltage will be mentioned in the question. They will mention all the values, and then you just have to find the current equation I in terms of T. Alright, so using all this info in the question, first I just substitute it one by one. We now would have 3 di dt plus with 12i equal to 4. So from this differential equation, we have to find I in terms of T. What is I in terms of T? The current equation. Given that when I is 0, T is 0. That's the inertial condition. We will use it to find constant C after this. And then what happened to the current after a long period of time? And then we have to use this current equation to solve that part. Alright. So now first we have to solve the DE part first, differential equation. As I mentioned before, we will use integrating factor method. So remember 5 main steps for this. Start with the first one, S. S stands for standard form. For standard form, derivative must remain as a single derivative. We now have extra constant of 3. So to eliminate that means that every single term have to divide by 3. Now we would have di over dt plus 4i is equal to 4 over 3. And now we already obtained the standard form. Okay, moving on to the second step, I. What is I? We have to find the integrating factor. What's the formula? What is the formula? Exponent to the power integral. So what do we want to integrate? Remember, it lies on denominator part, in this case dt. So that will be dt. So how do we find the function? Remember, focus on the second term here, what I circled in a green color. Eliminate variable that we don't want to use. In this case, because we want to integrate with respect to dt, we don't want to integrate I variable. So eliminate that part. We only choose the remaining part. So we only want to integrate 4. So integrate this out. We will obtain exponent to the power of 40. And that would be our integrating factor. Next part, M. What happened with M? M would be multiply. What do we multiply? The first step with the second step. So we would have di over dt times with exponent to the power of 40 plus with 4i times with exponent to the power of 40 equal to 4 over 3 exponent to the power of 40. Settle with the third step. Moving on, next part, for step B, we have to perform product rule. What happened here? So focus on the first term, what I boxed it in green color now. Factorize outside our derivative d over dt. So I factorize that out, what I highlight in yellow color. And then the remaining term, you just have to copy it back. So we have I e to the power of 40. So for the second term here, for I exponent to the power 40, you just ignore it. Hiraukan dia, tutup dia, ignore terus. And what happened on our right side? We only have to copy it back. So that happened for the fourth step, product rule. Alright, now moving on to the last step. I means that we may now start integrate both sides. So integral of d over dt of I exponent to the power of 40 dt. We want to integrate variable t. And then same thing happen for right side. We want to integrate 4 over 3 exponent to the power of 40 dt. Okay, now we have to solve this up. For left side, we have to integrate and differentiate the function. So it just cancel with one another. Copy it back. So we have I exponent to the power of 40. For right side, we can now integrate our exponential function. And then we may get exponent to the power of 40 over 3 plus c. Don't forget, we have a plus constant here. Okay. Now, how do we find constancy? That's the use of initial condition. In the original, they said that when our current is 0, times is 0. Substitute this up, we may get 0 is exponent to the power of 0 over 3 plus c. So, finally, c here would be negative 1 over 3. So, I substitute back c into our answer. So, I e to the power of 40 is basically exponent to the power of 40 over 3 minus 1 over 3. Okay. So after that, we can make I or current as our main subject because that's what the question asked for. And I can factorize out 1 over 3. So finally, current is basically 1 over 3. Exponent divided by exponent, it cancel out with one another. So we have 1 minus with 1 over exponent to the power of 40. And that's basically our current equation. So last part of the question, they ask for what happened to the current. So what happened to I after a long period of time? So means when our time is infinity. So remember here, alright, so for the last part, this can be rewrite to exponent to the power of negative 40. And we know exponent to the power of negative infinity, I rewrite here. Exponent to the power of negative infinity actually goes to 0. So what happened to the current? Means that for the current part, we would have 1 minus 0. So means that our current would remain at 1 over 3 as time goes to infinity. So that's all for application of differential equation.